Hello everybody. I hope you're doing well. If this is the first time you're on this channel, my name is Amir Kiani and I'm the host of the Virtuous Machines podcast. In this podcast, we explore the intersections of AI and philosophy, questions about ethics, safety, consciousness, and so on. If that's something you're into, make sure to subscribe to the channel to stay up to date on the next videos. Alright, I'll see you on the other side. Today we're diving into a fresh paper by Meta AI, authored by Quentin Garrido, Yann LeCun, and other colleagues. The title is Intuitive Physics Understanding Emerges from Self-Supervised Pretraining on Natural Videos. At its core, this paper asks a very simple and yet bold question. Do machines need core knowledge built in order to understand how the physical reality works? We'll go a step by step. We'll first discuss the background, asking the question of what is core knowledge. Then we'll explore how this connects to AI's well-known struggles with common sense. We'll then walk into the setup of the study, look carefully at the results, talk about the weaknesses and strengths of the approach, think about the limitations and where this research is headed, and finally we'll reflect on the philosophical implications of this research. In developmental psychology, there's a long-standing idea called the core knowledge hypothesis. The idea is simple. Humans are born with certain innate cognitive systems that act as scaffolds for reasoning about the world. They're kind of like starter packs that evolution gave us, so we don't have to start everything from scratch when it comes to understanding the world. They're hardwired into our brain and into our body. Some examples include object permanence, which means that objects continue to exist even when they are hidden. For example, if you put a toy into a closet, children won't assume it's gone into another dimension. They expect it to still be there. Another example is continuity. Objects move along continuous paths. For example, if a ball rolls behind the screen, it shouldn't suddenly appear from the other side of the screen. There should be a continuation between the two sides of the screen. The ball should go through before appearing on the other side of the screen. Another example is solidity. Objects can't pass through one another. Try pushing your hands against one another or against the wall or your table, and you won't see that they merge, they combine into one another. And babies seem to understand this pretty innately pretty early on in their development. Another example is gravity and support. Essentially, unsupported things fall. If you stack a block halfway on the ledge, babies expect it to fall if not supported. There are other examples and principles that we won't cover here, but essentially the idea is that all these principles are sort of innate in the baby's minds from early on in their development, and that's the gist of the core knowledge principle. In fact, research suggests that these aren't just human things. Primates, cows, or even chickens show some of these expectations. Essentially, these are some shared toolkit across a lot of species. Now, here's the big debate. Are these principles built in from birth, or do we learn them by watching the world? That debate between what's called nativism versus learning has been going on for a couple of decades now. Now, AI is stepping into the fight. Over the past few decades, AI has become shockingly good at doing abstract tasks, writing essays, solving math problems, writing code, summarizing legal documents, and so on. The kind of things all of us frequently use by ChatGPT, Claude, Gemini, or other large language models out there. But here's the twist. A lot of times when you ask them to do something simple, things like motion, direction, and a lot of basic physical facts that humans are quite well aware of, they will get it wrong. Like I said, this is especially true when it comes to mechanic and spatial reasoning. And in fact, robotics shows the same pattern. Only very few companies like Boston Dynamics have been able to create robots that move around and do things to a human-like grace. And even then, those robots don't really understand why their bodies stay upright or why their feet don't pass through the floor. This is generally known as Moravec's paradox. Hans Moravec, a roboticist from the 80s, noticed something strange. Tasks that are easy for humans, like perception, movement, and physical intuition, are the hardest for the machines. Meanwhile, things that are pretty hard and complex for humans, such as playing chess at a grandmaster level, turn out to be a lot easier for machines to learn. Alright, now let's discuss how this paper actually tested the question that we're interested in. Researchers built a model called V-JEPA, which stands for Video Joint Embedding Predictive Architecture. The name sounds complicated, but the idea is fairly simple. Here's the core trick. First, the model watches a lot of videos. Parts of each video are hidden. Imagine chunks of the screen are kind of blacked out. Now, instead of trying to guess the missing pixels, like filling the picture at the lowest level, the model tries to guess what's missing in a more abstract representation space. To put it simply, most older video models are kind of like kids who try to redraw every dot in a painting. V-JEPA, on the other hand, is more like someone saying, oh, this is a cat walking across the room. I don't need to know the color of every pixel. I just need to know the cat keeps walking forward. See the difference? That difference of predicting meaning instead of pixels turns out to be pretty powerful. Now, how do you test if this model has learned anything about physics? Researchers borrowed a clever method from infant psychology called the violation of expectation, or VOE paradigm. Here's how it works with babies. In the quote-unquote possible video, a ball rolls behind the screen and comes out the other side. In the impossible one, the ball rolls in but never reappears. Babies turn out to stare longer at the impossible videos, as if to say, wait a minute, that doesn't make sense. The researchers applied the same logic to AI. They showed V-JEPA both possible and impossible videos. Instead of staring longer, the AI showed its surprise through prediction error. Its guesses about the hidden parts were much worse when it came to the videos that violate physics. Think of prediction error as the AI's way of raising its eyebrows. Figure number 1 in the paper shows this exact process. On the left, we have the evaluation setup with benchmarks. In the middle, we have the training loop with the masked video prediction. And on the right side, we have the surprise score across time. Okay, now here's the trick then. The AI gets surprised when the physics is broken. Just like babies stare longer at impossible events, V-JEPA produces higher prediction errors when the ball vanishes. That surprise, my friend, is the fingerprint of intuitive physics. Alright, so V-JEPA is clearly impressive, but just like any other system, it has its strengths and weaknesses. Let's break these down. First, let's see where V-JEPA shines. First is object permanence. It knows that things don't just blink out of existence. If the ball rolls behind the couch, the model expects it to come out of the other side. Then we have continuity. Objects move around continuous paths. A ball doesn't teleport from one side of the screen to the other side without traveling the path in between. Third one is support and gravity. It understands that unsupported things fall. Finally, we have inertia. If something is moving, it keeps moving until something else stops it. So in many ways, V-JEPA has picked up many of the basic rules about the physical world that infants and even some primates have. But now let's see where the model stumbles. First one is solidity. Sometimes lets objects pass right through each other, which in reality they shouldn't. The second one is collision. Even when it does notice contact, it doesn't always get the details right. For example, where should the balls continue their path after collision? Or how do they bounce between each other or the other objects in the environment? If the color of the object changes, sometimes the model struggles to track it, even though that's not an issue for humans. So in short, V-JEPA is really good at some of the basics, such as object continuity, permanence, and gravity. But when it comes to finer details of interactions, such as collision or identity over time, it struggles. Hey everybody. If you've been watching to this point, I want to thank you deeply, because according to YouTube, most people don't make it to this point. I also want to ask you, like a friend, support me and this podcast in any way you can, by subscribing to it, sharing it with anyone who might be interested, or liking the videos if you think they add value to your life. Also, if you know people or organizations who might be interested to be on the podcast, support it, or help me grow it, please make sure to get in touch, either through the comments or just by shooting me an email to amir@virtuousmachines.com. I'll make sure to put a link to the email as well as my website in the description of the video. The authors of the paper are careful to note, V-JEPA is not perfect. It only works with short 3 to 4 second clips. It can't yet build long causal chains, and it's a passive observer. It doesn't interact. Imagine trying to understand gravity only by watching 3-second videos. You'll get some of it for sure. I mean, things fall, things move, but you'll miss more complex events, like a whole stack of dominoes collapsing one after another. That's where V-JEPA struggles. Okay, here's the philosophical punchline. Core knowledge hypothesis stipulates that infants are born with internal expectations of basic realities of the physical world. Things like permanence, solidity, and causality. But V-JEPA shows that you can actually learn these expectations without having them innately hardwired into your system. Just give a predictive learner enough data and they will actually learn it. So as you can see, this raises a challenge to the strong nativist view. It doesn't disprove human core knowledge, but it suggests that it might not be necessary after all. Now, this echoes the old debate between nativism and empiricism. Nativists like Descartes, Kant, and Chomsky said that some structures have to be innate. Empiricists, on the other hand, such as Locke and Hume, said that knowledge comes from experience. So if Kant says that human mind imposes categories like causality onto the reality, V-JEPA says maybe not. Maybe causality isn't imposed by mind in the first place. Maybe it is learned from the world. That's an interesting philosophical implication, which I have a lot more empathy towards, because as someone who studies philosophy professionally, my view is closer to what is known as realism, where we sort of observe the reality out there and try to understand it, as opposed to imposing things onto reality by our mind. I know it's a huge topic and there's a lot to discuss, but I wanted to mention that this paper and its results would presumably resonate with a flock of philosophers such as myself who have a stronger empathies for things like realism. But in any case, if you find this topic interesting, let me know in the comments and I'll record an episode about it. Alright, I hope you really liked this episode. If you did, make sure to like it, share it with anyone who might be interested, and subscribe to the channel to stay up to date on the next videos. As always, if you have any suggestions, questions, or thoughts, make sure to comment on the video. And finally, if you are or know somebody who works in these areas and you would like them to be interviewed on the podcast, please let me know. Alright, awesome. Thanks for tuning in, everybody, and I'll see you in the next episode.